Welcome to the first lecture in Descriptive Geometry. Descriptive geometry provides the geometric foundation for representing three-dimensional objects on two-dimensional engineering drawings. Although modern engineering relies extensively on CAD systems, the principles governing technical drawings remain unchanged. This course develops the methods used to represent and analyze geometry in space. Particular emphasis is placed on developing spatial reasoning, the ability to interpret two-dimensional drawings as three-dimensional geometry, and to represent spatial relationships accurately through orthographic projections. The course begins with the projection of a single point and progresses systematically through lines, planes, and increasingly complex spatial constructions. Throughout the lectures, the emphasis is placed not only on graphical procedures, but also on the geometric principles that govern them. Before we begin studying the methods of descriptive geometry, it is worth asking a simple question. Why was such a method needed in the first place? For centuries, builders, craftsmen, and architects relied on sketches, physical models, and practical experience to communicate their ideas. These methods served their purpose, but they depended heavily on personal interpretation and offered no universal graphical language. During the 17th and 18th centuries, science and engineering advanced rapidly. As machines, structures, and manufacturing processes became increasingly sophisticated, the need for a precise and standardized method of graphical communication became evident. The development of such a method is closely associated with the French mathematician and engineer Gaspard Monge. In the second half of the 18th century, while teaching at the military engineering school in Mézières, Monge developed a systematic approach for representing three-dimensional objects and solving geometric problems through projections. The central idea was remarkably powerful. A three-dimensional object is represented by orthographic projections onto mutually perpendicular projection planes. The projection lines are perpendicular to the corresponding projection planes. By combining these projections, the spatial relationships within a three-dimensional object can be represented accurately on a two-dimensional drawing. This geometric framework became the foundation of descriptive geometry and remains fundamental to technical drawing today. Okay, now that we understand the historical background and the basic idea behind Monge's method, let us begin to get familiar with the system and learn how to use it, step by step. We begin with three mutually perpendicular projection planes: the horizontal projection plane, known as pi1, the vertical or frontal projection plane, known as pi2, and the profile projection plane, known as pi3. These three planes are established within a theoretical three-dimensional space. Together they divide this space into 8 infinite regions, known as octants. The planes intersect along 3 coordinate axes, which meet at a common origin and define the directions of the coordinate system. Their positive directions follow the right-hand rule. For our drawings, however, we need to transform this three-dimensional arrangement into a two-dimensional system. We do this by projecting the 3 planes onto a common plane. For practical reasons related to technical drawing, the frontal projection plane, pi2, is commonly chosen as the drawing plane, the fixed reference plane to which the other projection planes are unfolded. Therefore, pi1 and pi3 are rotated into alignment with pi2. This is a conventional choice rather than a theoretical necessity. During this operation, the horizontal and profile planes are rotated about their respective lines of intersection with pi2. As the planes open out, the three-dimensional system becomes a single two-dimensional drawing surface. In the particular configuration shown here, an important consequence of this operation is that the y-axis is represented twice in the unfolded system. This occurs because the y-axis is the common line of intersection of pi1 and pi3. As these two planes are unfolded onto the fixed pi2, their respective representations of the y-axis extend in different directions in the resulting two-dimensional system. Once the system is fully opened, 4 quadrants become visible. 3 of them correspond to the 3 projection planes, while the 4th is an empty quadrant, a region that does not represent a projection plane. Understanding this arrangement is essential. From this point onward, every projection we construct will be positioned within this system, and its location will carry precise as spatial information. Okay, now that we understand the structure of the projection system and how the planes can be unfolded, let us establish a few fundamental principles before looking at some examples. First, we need to distinguish between projection directions and the viewing direction of the projection system. In orthographic projection, an object is projected onto a particular projection plane along lines perpendicular to that plane. The projection direction, therefore, belongs to the process of representing an object on a particular projection plane. It should not be confused with the direction from which we observe the projection system itself. The viewing direction is determined by the side from which we look at the projection system. When looking toward the frontal plane, pi2, we can view it from either its positive y side or its negative y side, since the y-axis is perpendicular to pi2. In the previous slide, we established the configuration used in our representation. Pi2 was selected as the fixed reference plane, and the system was opened while viewed from the positive y side. Second, each specific combination of positive and negative directions of the x, y, and z axes identifies one particular octant. The 3 coordinate directions together determine which octant is being represented. Now let us look at 2 more examples and see how the unfolded configuration changes for different octants. First, let us open the 4th octant, positive x, negative y, and positive z. This octant is located on the negative y side of the frontal plane. Therefore, when viewing the frontal plane from the side on which this octant is located, we view the system from the negative y side. From this viewing direction, the positive x-axis appears to the right, while the positive z direction remains upward. We now open the system while viewing it from the negative y side. As established previously, pi2 remains fixed, while pi1 and pi3 unfold about their respective intersection axes with pi2 until they coincide with it. Now let us look at the 5th octant, positive x, positive y, and negative z. This octant is located on the positive y side of the frontal plane. Therefore, we view the system from the positive y side. From this viewing direction, the positive x-axis appears to the left, while the negative z direction extends downward from the origin. We now open the system while viewing it from the positive y side. Again, pi2 remains fixed according to the unfolding arrangement we established, while pi1 and pi3 unfold about their respective intersection axes with pi2 until they coincide with it. In the resulting unfolded configuration, the positive x-axis appears to the left, while the 2 y-axis representations extend upward and to the right from the origin. By comparing these examples with the first octant, we can now see how the spatial position of an octant determines the side from which we view the system when opening it and consequently affects the orientation of the resulting unfolded configuration. All right, let's do a short independent exercise for about 20 seconds. Let's take the 8th octant, and the question is, what will its unfolded configuration look like, assuming that the frontal plane, pi2, is the fixed reference plane? Assuming that the frontal plane, pi2, has been selected as the fixed reference plane, we view the 8th octant from the negative y side. The resulting unfolded configuration has the positive x-axis pointing to the right, the negative z-axis pointing downward, and the two representations of the negative y-axis extending upward and to the left, respectively. Good. Let us summarize this introductory lecture. First, we explored the historical background and the need for a systematic method of orthographic projection. Second, we became familiar with the theoretical three-dimensional space and focused on how the spatial regions that make up this space can be unfolded into a two-dimensional representation. Third, we established the distinction between the objective projection directions, which are determined by the projection planes, and the viewing direction used to observe the unfolded system. Since this is a recorded lecture, you can always return to any part that was not completely clear, review the explanation, and go through it again at your own pace. In the next lecture, we will begin projecting individual points within the system. A point is a dimensionless geometric entity that represents a specific location in space. Before we finish, I will leave you with 3 questions for independent practice. First, what will the unfolded configuration of the 6th octant look like when pi2 is selected as the fixed reference plane? Second, what will the unfolded configuration of the same octant look like when pi3 is selected as the fixed reference plane? Third, what will the unfolded configuration of the 3rd octant look like when pi1 is selected as the fixed reference plane? Thank you for your attention. See you in the next lecture, and until then, take care.